Good afternoon, everyone. It's exactly 12:03 p.m., nicely on the east coast of Australia. Welcome to a webinar organized by Geofabrics in partnership with Solmex. We are going to give you some understanding on enhanced lateral drainage geosynthetic products. My name is Rajesh Bausa. I'm working as a General Manager, Business Development and Technical for Geofabrics. And I'm your host today. Let me introduce you to today's two speakers. Actually, it's not only Rene. We are having also another speaker from Solvex Tenkate joining us. So Rene, let me introduce Rene first. Rene is Technical Marketing Manager for Solmex, based in Canada, but we are lucky to have him here in Australia. He's working with Solmex for a long period of time, but in addition, he have a minimum or more than 20 years of experience in geosynthetic industries. His whole experience comes from working with different manufacturers and suppliers in Canada as well as US. So he have a wealth of experience, particularly talking about geosynthetic materials and applications and his functions. Second speaker is Tony, who is a senior technical engineer for Solmex, based in Malaysia. He also have a wealth of experience using different geosynthetic materials in civil engineering application. What I would like to ask you before Rene starts the presentations, please put all the question in Q&A. Don't put in your chat sections. Please raise your question in Q&A. And just let everyone know that this webinar is recorded and it will be available through Geofabrics Academy website. Thank you all. Thanks for attending. Rene, you can start your presentation.
Excellent. Thank you very much, Rajesh. Welcome, everybody. I'm going to jump right in here on this my talk here on providing resilience to civil structures through the use of an enhanced lateral drainage geosynthetic. Some of you may not be as familiar with Solmax. So Solmax is the agglomeration of 4 different companies, geosynthetic manufacturers. As a company, Solmax has been in business for over 40 years with over 2,000 employees spread out around the globe. In terms of production capacity, we have the ability, the capacity to produce in excess of 300 million square meters of geosynthetics per annum. And we have 20 geosynthetic manufacturing facilities spread out throughout the world. As you can see on your screen, there are certainly several that are located in Asia Pacific. We are the largest manufacturer of geosynthetics globally. And we have the privilege of being able to serve our markets in just about every geosynthetic capacity that there is. Not going to spend too much time reading, all of these, the self-promotional slides here, but it's just to give you an idea of the scope, because some people might be more familiar with companies like Tenkate or than Solmax, but Tenkate is now a part of Solmax. So just to give you a bit of an idea of the size. Well, one part that I'm very, quite excited and proud about is this here, where we have in excess of 270 patents currently in the marketplace, which means that for us, innovation it's part of our bloodline. It's something that's extremely important to us. If we look at our mission statement, this really reflects what we are as an organization. We're all about enabling the sustainable construction of an environmental and civil infrastructure for tomorrow. And that's really the whole definition, or that's part of the definition of sustainability. It's all about meeting the needs of the present without sacrificing our children's and grandchildren's ability to have the same, access to the same types of resources that we've had over the generations. But sometimes sustainability, resilience are used almost at the same time, but they're not exactly the same. So I touched on sustainability, but resilience is more about the capacity of a system to withstand and to recover from any kind of disturbances. And when I was doing some more reading in this, there's a piece of reading that I really enjoyed. Gentleman by the name of Michael Bruno from the University of Buffalo in the US broke resilience down into 4 parts. So the first 2 parts are about what are the desired ends that we want via resilience. And in this case, we're talking about robustness and rapidity, and I'll define those a little bit more here in a second. And to get these ends, you have to be able to measure them. And the way that we measure how resilient a system is through redundancy and resourcefulness. So when I talk about robustness, it's really about the ability to withstand any kind of unforeseen demands on a system. Rapidity is about restoring a function that's been put under duress and restoring that function as quickly as possible. Redundancy is the ability or incorporating something in a system that allows or tolerates the loss or damage to a component. So if something gets damaged, something gets lost, there's another part of the system that can kick in and actually allow for that system to continue working the way it's intended to. And then resourcefulness is, it's one of the simpler portions in so many ways. It's the ability to identify a problem and then to respond to it quickly and effectively. So for a system to be resilient, let's look at roadways specifically. And to quote Sun Tzu's Art of War, it's all about knowing your enemy. And when it comes to roadways, when it comes to civil structures, by far the #1 enemy for these structures is it's water, it's moisture, it's water, any of those forms of hydration into the system is something that we're trying to get away from. So anything, any system, any idea that can help remove or prevent the water from getting in, and if it does get in, to actually remove it from the system as efficiently, as quickly as possible. And so the purpose of this webinar here today is really to discuss this system that we have. We call it MIRFI H2RX. And from here on in, just to keep this a little bit more generic, I'm just going to refer to it as an enhanced lateral drainage geosynthetic, or an ELDG. So what is the ELDG? First, what you'll see is it's a woven geotextile. And it is a multi-layered woven geotextile, and it has 2 very distinct components that you can see here. The first one, these are black polypropylene yarns. These polypropylene yarns provide the reinforcement and the stabilization function of a high modulus woven geotextile. The blue yarns, these texturized yarns, this provides what I like to call the magic with the water. It provides the moisture management or the wicking ability of the fabric. And so what that now provides for designers and for owners and anybody who's involved in these types of projects is all the functions that are required for a roadway or civil application for geosynthetic. It gives us excellent separation, filtration, reinforcement, confinement, and also now an enhanced drainage application that we have coined the term moisture management, because this is literally about constantly monitoring or managing, I should say, the moisture and drawing it out of a civil structure. In terms of how it works, keep it as basic as possible here. Polypropylene is a resin that is produced as a byproduct from the natural gas and from the oil industries. And so basically, if we think of polypropylene as solid oil, polypropylene is hydrophobic, it has no affinity for water. And in fact, at a molecular level, it repels water, it pushes it away. The filaments that we have are hygroscopic, the moisture management filaments. And each roll is woven so that there are in excess of 10 million of these filaments in every, I apologize for the North American vernacular here, in every 4.6 meter by 91 meter roll. And each filament is in fact the size of a human hair. So what that means now is that they're very small, they're very closely knitted together, which means they have a lot of affinity for capillarity. If we just take a quick look at the technical data sheet, the first thing you'll notice is that the product is completely biaxial in both directions. So in the machine direction, as well as the cross machine direction, which is MD and CD, they are completely biaxial. So they're independent really of traffic in terms of how they're located on a surface. And they have this ability to be able to draw water via capillarity against gravity, and that's part of the specification of the technical data sheet. There's actually wet front movements that you would see in the technical data sheet. So how does that actually work? Well, you install the fabric. Usually it's going to be between the subgrade and the base course, but it can also be between the base course and the sub base. It's really dependent on what the actual purpose, what the application of the project is. And what it does is it intercepts water that can actually come through pavement cracks or through shoulders. But not only that water, but it also intercepts water that's rising through capillary action. And then once that water has been intercepted, it actually draws it apart or draws it out of the roadway. And the question now becomes, well, how does it do this? How is that moisture drawn out of harm's way? And it all has to do with relative humidities and suction. So suction in a soil is inversely proportional to its relative humidity. So if I look down at the water table where I have relative humidities in excess of 99%, you'll see that you get very, very low suction levels in the order of 10 kPa. When this water, when you get this capillary action, as it rises up in the roadway itself, the higher up you get into the structure, the suction, the relative humidity tends to be a little bit lower. So you might be at 90% relative humidity. And then within this zone of influence that I'm going to discuss a little bit further here shortly, the suction can actually increase by 2 orders of magnitude compared to the water table, which is why now you start to have a draw and an attraction of the water up towards the fabric. And then moving out of the roadway, once you expose, let's say, the tail of the fabric to the atmosphere, you have suction that can be in excess of 10,000 kPa, so another order of magnitude greater, because the relative humidity is typically under 90%. And that's how the suction is being done. So to give you an example of what this looks like, we're putting some water in this little container here on the right-hand side. And so once the fabric is completely submerged, you'll see that the relative humidity of the fabric on the right side is 100%. But you can see that because on the left side it's been left exposed to the air, it's got lower relative humidity, which means now the water is being drawn over to the edge. And you can just see here at the end of 5 minutes how the water is starting to come out of the fabric. So one of the simple demonstrations that the University of Texas at Austin did a few years ago is they did these water transportation tests. So on the left-hand side here, you see there's a container full of water, and they have a black light, which explains this glow in the water that you see here. And there's the H2RI that has been placed in the container and then brought down, drawn across, and then we put a little speed bump right here and allow it to go across. And so when you watch as the water's being drawn across, there's a couple of things I want you to pay attention to. First thing is that the water had no issues, no problems with overcoming the speed bump, and it continued and made its way across. In addition, you'll notice that the table underneath the textile is completely dry. Any of the moisture, any of the water that gets in the fibers stays in those wicking yarns because of its hygroscopic nature. It draws it to it. The suction is greater than the ability of the water to be removed. If I do the very same test this time with a non-woven geotextile, what you'll notice is as this water progresses, a couple of things. You'll see that once it hits the speed bump, it stops. And then on top of it, because this non-woven geotextile is made out of polypropylene, which is hydrophobic, it releases the water. Once all of the pores are full, the water is simply released back. So it does not have this ability to wick over any kind of significant distances. This is really drainage with the help of gravity. So why is this, one reason why this could be important is, to give you an example, you design a road, you design this beautiful road, you've put in 2 to 3% crossfall. So this is what you've designed. And again, once we're out in the field, designs and reality are not always the same. What ends up happening is you end up with these uneven spots in the road where you can have a divot, you can have a little bit of a rut, and then the water wants to stay in there. And if the water stays there, as the traffic loads start to travel over top, it's going to make this area much softer because the water is going to make this subgrade that much softer. But by placing a product that has this capillary action, what ends up happening is the water is now going to be pulled out and drained out via a combination of the crossfall, but even more so by the suction, by the natural draw of the fabric. So what makes this product truly unique? This was a very simple test that revealed so much to us, again, many years ago. The University of Alaska Fairbanks did a test, and what they did is they took these containers of silt and saturated the silt. So this is a 200 millimeter tall container of silt. And what they did then is they placed on tables underneath, they put a geomembrane, and they put 4 different geosynthetics, one at a time. They put 2 woven geotextile, they put the geocomposite, a geocomposite product, and they put the LDG, or the H2RX. And then what they did is they took those saturated containers of silt and flipped them over, and they put them on top of each of these geosynthetics. And the idea is they measured the moisture contents throughout that 200 millimeter height. So if you get drainage that is strictly due to gravity, you should get the same moisture content throughout that entire column. So as it's progressing, you should get the same moisture content if it is strictly drainage via gravity. But what they found was that, in fact, the ELDG provided more drainage. It provided anywhere from 3 to 6% more moisture removal than any of the other products, including the geocomposite, which is a very large opening drainage product. And so it can certainly move a lot of water, but it wasn't moving more water than any of the other products, except for the ELDG. And their conclusion was that the difference between these products was the ability of the ELDG to remove water in unsaturated conditions. And what I'm hoping here is that we have some geotechnical engineers that kind of, give a little raise of the eyebrow, and hopefully that resonates with you, because it's one of the most complicated things for geotechnical engineers. The subject matter of unsaturated soil mechanics is a very complex one. So, but there are not a lot of systems and technologies out there that can remove moisture in unsaturated conditions. And the LDG is actually the only geosynthetic that does that. So why is it important to get soils or granular materials below saturation levels? Well, Harry Settergren, this is a gentleman that was a civil engineer that was an expert in seepage analysis, and he wrote a book on the drainage of highway and airfield pavements in 1987. And one of the statements that he made, which is very powerful, is he stated that the pavement service life could be reduced by half if the pavement approaches saturation only 10% of the time. So that's 5 weeks of the year. Now, I know we have people from all over the place here, but I would imagine, maybe except for Western Australia, there are several areas that do see a lot of rain where pavements can become saturated, again, 5 weeks over the course of a year, not 5 consecutive weeks, but just 5 weeks total. So that's on the granular side of things. Now, what about fine-grained soils? Well, according to Muni Budu's textbook on soil mechanics and foundations, he indicated that the undrained shear strength of fine-grained soils can increase by 20 percentage points for every 1% reduction in moisture content. So that 3 to 4% moisture content drop that I showed you in that silt column, when I originally saw that, I wasn't that excited about it. I didn't realize the implications. But based on Budu here, that means that if you can take 3 to 4% of moisture out of a silt, for example, or fine-grained soil, you can increase that soil's undrained shear strength by up to 80%, and that is substantial. Okay, so that's a little bit of the background how the system works, and the kind of the physics behind it. Few things that I'd like to be able to show and explain here. The way that the yarns are woven, they are woven in what we call the cross machine direction. So it's against the direction that we roll the fabric. So what that means is when this product is installed on the roadway, it should be installed and rolled out in the direction of travel if you want to evacuate the water into the ditches. Okay, so that's number one. Number two is these products require an overlap. And typically overlaps, we only worry about the quantity of overlap, which is usually 300 to 900 millimeters. And that's a function of the subgrade strength. However, with the ELDG, it is also important to think of overlapping it like the shingles on a roof. So you always want, if you've got, if you follow my hand here, if you have the water that's traveling from this hand, let's say, to this hand, you want the overlap to be shingled just like on a roof, because otherwise, if you go the other way, there's a potential of when the water drips out at the end here, it just feeds it back into the subgrade. So always think about it in terms of shingles of a roof, and you can see two examples of that on this page. Typically for edge details, there are several ways that we've seen it installed, and they all seem to work to one degree or another. So in this case, on this photo, this is a photo that was taken in Alaska. This is the first commercial installation that we ever did in the Americas with this product. And what they basically did in this case is they just covered up the edge with a more of an open graded aggregate to allow for that higher suction to happen because of the lower relative humidity. Using an open graded aggregate is a good practice because what that does is allows also for air to travel through and accelerate the drying process on the edge of the fabric, which accelerates the drawing the moisture out. Other ways of doing it, you can see in this case, you can actually drape the fabric along the edge of a roadway. And in that case, we again recommend putting a protective cover on top, again, an open graded aggregate. It protects it. It protects the fabric from mechanical damage from mowing operations or for animals or for people that get curious and want to start pulling on things. And it also protects the fabric from UV degradation. Another example here, if you don't have an outlet, you can again edge terminate it. And if you do have the option of, let's say, terminating it into a French drain, it's a great practice because all you need to do is the fabric comes along and you drop it into the drain itself, and that head differential by dropping the fabric will cause suction, will cause that water to be drawn out. Okay, so just a few examples on installation details. So I'm going to geek out here for just a couple of minutes. Soil water characteristic curves, they're not used incredibly commonly. They're a very powerful tool, but they're time consuming and expensive to generate. What these do is, this is a set of curves that will quantify the relationship between the internal suction, the matrix suction of the soil, and its water content. So if I look at a soil here and I see that my degree of saturation from 0 to 100 on the right side, if I have a saturated soil, essentially for all intents and purposes, there's no suction in that soil. And as there's suction applied, or as it starts to dry out, the moisture content hits a point where it does drop. And this point of inflection, not inflection here, this point here, which is essentially the intersection of the asymptote between this portion of the curve and this portion of the curve, we call that the air entry value. And that shows the matrix suction that's required to cause the desaturation of the largest pores. And afterwards, once you get much beyond this point, then the law of diminishing returns kicks in, and no matter how much suction you apply, you cannot completely dry out a soil or a granular material, which is why you never get 0% in the field. Well, you can do that with geosynthetics as well. So the ELDG, we generated the air entry value. The one that's of real interest and importance to us is this one right here. This 250 kPa value of air entry value, this is actually a fair amount of suction that the fabric can generate in contact with the soil. If I compare that air entry value to a non-woven geotextile, you'll see that the air entry value of the non-woven geotextile is basically, it's well under half of a kilopascal. It has no real affinity to draw moisture out. And that's because, again, this is a product that's made out of polypropylene typically. Now, we can do this with a bunch of soils. So I did a whole bunch of very technical research, which is my way of saying I Googled a series of generic soil water characteristic curves for different soils. So in this case, you see a clay, you see silt, and a granular base. And if I draw a vertical line from the horizontal axis at 250 kPa until it hits every one of these different materials, what that allows us to do, or allows me to quantify, is, in theory, in this case, how much moisture could I possibly draw out of each of those materials from their saturation points. So in the case of granular base, I could reduce the saturation, the moisture content by about 7%. In the case of silt, it could be, in this case, about 10%. And for the H2RI, we are looking at, or the LDG, we're looking to up to 4%. Okay, but again, remember that textbook from Voodoo. Every 1% reduction in moisture can lead to about 20% reduction in moisture content. So this is very unique. I'm hoping you're starting to get the flavor of this, is that, again, it's a product that can really start to benefit your roadways, because you're now stabilizing, you're hydraulically stabilizing on top of mechanically stabilizing your subgrade and your base course. So situations where the ELDG could be considered, you can read them all here. Areas with high water tables, excess moisture in basins, subbases, and in subgrades, for expansive soils, frost susceptible soils. Here, you might not care too much about that. Where I live in Toronto, Canada, we have frost susceptible soils, and we have a lot of cold. It can be used as an anti-capillary barrier. Basically, this is the kind of product that you should, or system that you should be considering anytime you are in a position where moisture could negatively affect your civil structure. So I'm going to look at some research projects that will focus around these main points here. So if we look at some of the research results over the year, and a lot of this is done out of the Americas, but we've been researching this product for almost a dozen years now. So this is just a very brief cross-section of some of the research results. So one of the things that it does is that we found that it normalizes the moisture content in expansive clays. And I'm going to get into these individually here in a moment. It also lowers the moisture content in the base course below optimum compaction levels. It has an effective zone of influence of approximately 200 to 250 millimeters above the location of the geosynthetic. That's in the base course itself. And it also allowed us to, the researchers, I should say, allowed us to actually quantify the moisture management benefit to flexible pavements. And then finally, we have the ability to use the ELDG as an anti-capillary barrier. So let's look at expansive clays. So the University of Texas at Austin did a research project just outside of Austin, Texas. It was an expansive clay project on State Highway 21. And here's a typical highway over there. What's interesting about this is this particular photo was taken barely a year after this highway was built. So that's how aggressive their expansive clays are. And those longitudinal jointing cracks that you see here are very, very typical. So their way of addressing this, in this particular roadway, they wanted to do a lane expansion. So they're going to do a widening, a 2.7 meter widening. And this has got to be the most convoluted cross-section that I've ever come across in my career in this business. I'm not going to go through every single one of them, but you can see there are 2 layers of geogrid. There's different types of embankment materials. There's a cement treated base. There's different types of asphalt. And at the bottom, they had this layer of non-woven geotextile that was 2.7 meters wide. So the DOT, the Department of Transportation, allowed us to come in, and they told us, you can put whatever you want here. You can use any product you want, but you can't change anything else about the design. And they said, by the way, you cannot daylight the geosynthetic either, because we don't want to have animals choking or choking on after having chewed up the plastic. From an environmental perspective, they didn't want that to happen. So the geosynthetics had to stay buried, which didn't excite us very much, because we were wondering, how are we going to get that water to exit the fabric? So the test sections themselves, there were 4 of them. Each was duplicated, and they were 150 meters in length, laid out the way you see here. And then a series of moisture sensors were placed underneath each test section. Now, when it comes to expansive clays, or even pavement movement, if an entire pavement surface travels up or travels down together, nobody really cares. It's when you have that differential movement, that's where you get the cracking in the asphalt and any road building materials you have. So what we decided to do is we looked at all the data that was generated, and we plotted the spread in moisture content between each series of sensors for each product. So each product had 5 sensors. So we plotted what that spread was between sensors 1 through 5 for each individual product. And what we found was really interesting to us is the non-woven and the 2 high modulus standard polypropylene-based geotextiles all had high moisture content spread and a lot of variability. But when you compare that to the H2RI or the ELDG, they found that the moisture content spread was well under 2%, and then the overall variation was much less. And the conclusion of the master's thesis from the student that worked on this project was the ELDG showed the least amount of shoulder cracking with basically none at all, and that it was able to minimize that shoulder cracking by redistributing, by normalizing the moisture throughout the roadway. So it would sense moisture come in above it, it would attract it, and then because of that suction it would attract it to a drier area. And this is just a process that would continue to happen. And it really went a long way towards addressing those issues that they've had for years. In terms of lowering the moisture content and base course below compaction levels, time's not going to permit to get into the guts of how they did all the research, but the University of Kansas did some numerical analyses and some lab work, and they showed that the ELDG reduced the moisture content in the aggregate base in the order of about 2%. So then what they did is they took granular materials and put it in these triaxial testing apparatuses, and to determine at different moisture contents what happens to the resilient modulus of the base course. And what they found was that the more moisture that you could draw out, the higher the resilient modulus. But you see here, the optimum moisture content is 9%. That's only optimum for compaction. The beauty of it is if you can keep drawing moisture out, even after installation and compaction, you have a great chance of improving the resilient modulus. So in this case, by reducing the moisture content by 2%, they showed that the resilient modulus would increase threefold. And the permanent deformation was also reduced by 40%. So let's take this one step further here. What happens now, instead of having removed water, if we don't have a system to take that water out and we get a significant rainfall, that optimum moisture content now at 9%, if you only add another 2 points to it, next thing you know, your permanent deformation based on these triaxial tests goes up 5-fold. So any system that can constantly draw moisture out, pull more moisture out, is a very good idea. We know that the effective zone of influence is 200 to 250 millimeters directly above the LDG. And I'm going to talk about what that, the significance of that in the next section here, quantifying the moisture management benefit to flexible pavements. So some of you may not be familiar with this equation. This is the standard AASHTO equation that's used in the Americas for flexible pavements. It's all about the predicted loading being a function of all these factors here. What I want to focus on really is the structural number. And the structural number itself is a function of a layer coefficient, of a layer thickness, and a drainage coefficient. So each layer, whether it be granular or asphalt, has a layer coefficient, a layer thickness, and a drainage coefficient. So when you look at that, you might be thinking that we address the layer drainage coefficient from a research perspective to try to quantify the hydraulic benefits. But in fact, what the researchers did is they said, let's look at the layer coefficient itself, and knowing that it's a logarithmic function of the resilient modulus of the granular base, what happens when we saturate this granular base and as we pull moisture out at the rate that we can with the ELDG, what ends up happening? So what they did is to incorporate these benefits of the hydraulic benefits. The first thing they did is they said the LDG is a polypropylene-based material. It provides mechanical stabilization, number one. So that mechanical stabilization, we call that a geosynthetic structural coefficient. So that's been in place for over 2 decades that we've been doing that. But from a hydraulic perspective, we look at 2 environmental parameters. We look at the number of days below freezing, because the system goes dormant at that point. Once you get 0 degrees, the water that could be in the fabric freezes, we're not removing it. And then we look at saturation rain events, because once you get your granular base is saturated, your hydraulic benefit is 1. And as it starts to dry, that hydraulic benefit increases, and eventually it'll hit an asymptotic point where it doesn't continue to increase. But before that happens, you get another saturation rain event, and then another, and another, and another. And with government data, you can actually get all this information to be able to quantify the amount of damage that's caused to the base course throughout. And so we selected a 5-year time frame to quantify all this information and to be able to quantify the damage to the base course for each of these saturation rain events. And that eventually led us to something called a hydraulic improvement factor. So that equation, which started off as structural number that's based on these layer coefficients and drainage coefficients and thicknesses, now can be improved by this geosynthetic structural coefficient and this hydraulic improvement factor only on the granular layer overlying the ELDG and only up to a maximum of 200 millimeters. That's where we drew the limit in our design software. And to give you an idea, again, this is for the Americas, but this is a bit of a heat map that shows you that the ELDG can be anywhere from 1 in this part of the country. And don't feel bad for those folks there, because there are no roads up here. It is too cold and nobody lives here. And it can go all the way down to up to 1.25 in places like Arizona, where it's very, very dry. I'd say for the majority of Australia, you're likely looking at this shade of green. So in the range of 111 to 115, as high as 1.25, let's say in Western Australia. Okay, and now the last piece of research I just want to go through very quickly here is this is a product that can also act as an anti-capillary barrier. Here's a large 200 millimeter diameter silt column that was a test was done on by the University of Texas at Austin. And you'll see here, water's being fed down the column, okay? I have a non-woven geotextile that's placed right here. Now, look what happens when the water hits that column. You'll see that it stops progressing. It stops and it's done at that point. And then after a while, the water starts and it moves through again. So what happens? Well, with the capillary barrier, with the capillary barrier, what happens is that the pore sizes within the soil are much smaller than within the geotextile. So they inherently have much higher suction, and the water stays, the moisture stays in those in the soil. But as the moisture content increases, that suction decreases until we hit the point where there's a breakthrough suction. And once we hit the breakthrough suction, that's when the water is allowed to flow again, and we now have saturated soils. Now, when they did this, they repeated this test again with the H2RI and again with a non-woven, but they shrunk the size of this soil column because it was taking too long to do the experiment. But what you'll notice is that the initial moisture content was 15%. And as they were feeding the water in the column, the moisture content increased to 30%. Well, at breakthrough, the non-woven, the water content climbed all the way up to 44%, which is basically saturation levels for that soil. And that was after 30 hours. While for the H2RI, we only had a slight increase up to 33%, and it increased, the breakthrough happened after 7 hours only. Okay. So Rajesh, I think I'm going to let Tony take over here to do the case studies, and then we'll wrap things up and we'll take some questions.
Right. Good morning, everyone. Thank you, Renee, for the insightful presentations. And I will take over now I would like to actually share 2 case studies. One is located in Thailand, and another one is located in Australia. So let's start with the first one. This is a ELDG site trial for road rehabilitations on National Highway number 117. And basically this project site is at Nakhon Sawan, and this is a province that is located at the northern Thailand that connect to the Fiji, if I pronounce correctly, and by this National Highway 117. And this highway was completed in the 1990, and it actually has a lot of problems like this pavement distress, and it requires repairs and overlaying again and again. And so the clients was intent to find a solution, and where the ELDG appears to be an innovation solution for this highway. Some project backgrounds. The highway was completed in 1997, then rehabilitated in 2021, but the pavement distress still happens after the first rehabilitations. And because of that, the highway is rehabilitated again in 2020 with the inclusion of ELDG. And just some basic information, it is a conventional flexible pavement with 4 lanes, 2 lanes to the northbound and 2 lanes to the southbound. And this highway has the average daily traffic in 2021 is about 21,500 vehicles per day. And the percentage of the heavy trucks is about 10%. Yep, as mentioned, after the first rehabilitation in 2021, pavement distress was still keep happening, such as like the longitudinal cracks, block cracks, aggregator cracks, and even the rutting is is in a serious condition. And this highway was also subjected to the flooding during the raining season, and it has a high groundwater table, which is about 2.5 meters below the ground. So the owner wanted to find the appropriate solutions to sort out the problem. And the first is to provide a good separation in between the new cement rock base and the existing subbase. Besides that, the client also wished to have the mechanical stabilization functions, as well as they want to remove or eliminate the water out from the existing subbase. And that is why this ELDG came in as one of the innovation solutions to solve these problems. The field trial of about 1 kilometer between station 140,000 to 14,000 to 15,000, where the monetary field infrastructures, the field monitoring instruments were installed, such as like the suction sensor, soil moisture sensors, as well as the horizontal inclinometer. And this is for the purpose to monitor the performance between the section 1 and section 2. Here, with section 1, the geotextile were installed, and the section 2 were the one without the geotextile. So just some photos to show you. The existing pavement will remove and start the installation of field monitoring instruments. And this video shows you how is the H12X or the ELDG will lay along the roadway to make sure the wicking yarn is across the roadway. After that, new cement base course were placed, and this was the elimination details in this project. Grab tank that under rock protection. Continue with the asphalt, and this is what I want to show you. When we look into the performance evaluations, and this moisture database shows you that it gives a very consistent moisture even after the rain event in the section 1, as you can see here. And for the section 2, it appears a sudden change after the rain event, and it takes a long time to back to the equivalent moisture level. For the horizontal inclinometer data, it appears the same. It gives you a quite consistent result, where the section 1 with a small movement compared to the section 2. Additionally, that the deflections of the surface of the road were measured before and after the rehabilitation works. And this graph shows you that about 30% reductions of the surface deflections after the rehabilitation works. The left photo was taken right after the constructions, and the right photos was taken after 3 months of the construction, and it shows no sign of pavement distress, and it works perfectly well, and the client was happy and continue with other section of the roadway. So the second case study I would like to talk about is the ELDG used in Australia in the local street that require upgrade, and the client was pleased to use this kind of system to deal with the soft and saturated site conditions. So the left-hand side photos is where the first section, the product is being laid, and it shows the mega flow drain on the left, where it's used as a drainage system to drain away the water from the roadside. And this ELDG products is installed and or contacted to these mega flow drains. And the right photos, where you can see, because the top layer of ELDG was laid to ensure the single arrangement, it is wrapped back, and after the laying of the second or the adjacent layer of the ELDG, and it put it back to ensure the single arrangement. And yes, the base course layers was placed over the road, and it is completed in the mean of the year for the half of the road with pavement. And the opposite sides is still under construction, and we will following up with the project teams, and we will collect the data as well. So now I would like to pass back to Rainey to conclude the presentation. Thank you.
All right, thanks, Tony. I'm actually not gonna go through the last of this the slides here, because it's already 5:02. All I wanted to really do though in the next few slides is just, you know, try to bring it back to this 4 hours of resilience. What I'm hoping that you got out of this is just this whole concept, this whole idea that if you want to be able to build more resilient infrastructure, sometimes you have to think outside the box and, you know, come up with some new ideas, some new technologies and concepts. And this ELDG, I'm a firm believer in the product and the system myself, and I've seen it do some absolutely wonderful things. So I want to thank you all for your attention. And Rajesh, if you want to unmute yourself and maybe come back on camera and see if there are any questions that need to be addressed, I'm just going to stop sharing my screen here.
Thank you, Rene. Thanks for a very informative presentation. As I explained to all of you attendees, if you have any questions, please raise in Q&A sections, not in a chat section. So I'm not at this stage. I haven't received any question yet. We still have 5 minutes. So anyone have any questions, please raise in a Q&A section so that I can ask Rene to provide some further information or answers.
Looks like we answered everything, Rajesh.
Looks like it, Rene. You provided each and every information, whatever they are looking for in your presentations. We still have a couple of minutes. If anyone have any questions, please do so.
Don't think we're going to get anything, Rajesh.
No,
I see something.
yes. Okay, Gary Matthews. Thanks, Gary. Rene, Gary is asking, could you please discuss a little bit more about bi-capillary barrier concept?
The capillary barrier. Okay.
Yep.
So let me just go back to those slides here. What's going to be, bear with me. Just going to scroll back up and I'll reshare the screen and show that again. Okay. And then share this one. So the whole concept here with the capillary barrier is, you know, suction within granular materials, and I'm going to count geotextiles as they're not granular, obviously, but they have openings within their pores. So any porous material, suction is going to be inversely proportional to the to the size of the pores. So because the pores are so much smaller in the soil particles that you can see here graphically showing, the water.
Sorry, Rene.
Yes.
You're not sharing your screen.
Oh, you know why? Because I'm a rookie. And there we go. Sorry about that, folks.
Thank you.
All right. So what you're looking at here is these pores are so much smaller than the openings, the pores within a geotextile, a typical geotextile, no matter what the material is. So what happens here is that this area, there's just higher suction. The water is going to be attracted through, capillary action, through surface tension to the soil particles more so than the geotextile fibers. And that's why when you saw that water, that video of the water coming down, that's why it stopped right above the textile. And it only proceeded once this whole area here became saturated. And it became saturated because if you remember those percentages, just before the water traveled through, the moisture content was 15%. Then as the water was traveling through, it was 30%. But the breakthrough moisture content here was 44%. And so that means now it's saturated, it's completely saturated. But bear with me, apologies. With the doing the same experiment with the ELDG, what we found was that this time was accelerated by a factor of 4. So instead of backing up for 30 hours and having over 40% moisture content, it only backed up for about 7 hours, and the moisture content was only about 33%. So that is a way of helping to prevent issues in the field when you have these kind of products. If you have a product that's got inherent moisture management built into it, you can help prevent these kind of potential capillary barriers or capillary breaks from happening.
Thanks, Rene. Thank you, Gary. I hope you got the answers. Yes, thank you. All right, I think so. We are nearly at the end of our webinar anyway. So let me wrap up this webinar. First of all, thanking Rene and Tony to share their experience and knowledge with us. And thanks to all the attendees for attending this webinar. Okay, sorry, one more question, Rene, if you want.
Yeah, it's I'm just reading it. They want to know, one of the attendees would like to know if they'll be getting certificates for their CPD hours.
Okay. Yes, we will share the CPD certificates with you. Please contact marketing@geofabrics.com.au for further information, and we will share the CPD certificate. No problem. All right. Thanks a lot. Thanks, everyone. We are finishing our webinar here. There are more webinars to come. So please look out for Geofabrics invitations, as well as just visit Geofabrics Academy website for further information. As I explained at the start of the webinar, that this recording will be available through our website, so you can visit anytime. Thank you all. Have a great day.
Thank you.